right. Like I said, when it gets to chapter 12, we have a pretty brief introduction to the topic of, I guess they call it prediction. Just to give you an idea, of course, you can always run with this and things get much more complicated. That's true for anything, really. What we're trying to do here is, if we look at the previous chapter, we can establish if there is some correlation between two variables. In this chapter, we now want to, by way of an equation, say exactly what the relationship is between, or what a good indication of the relationship is between two variables. For example, we can look at how SAT scores affect your GPA. So I have two variables. We have what's called the predictor variable, the one that is sort of the independent one. That could be anything. And I want to see how that affects what I call the dependent variable, or the criterion variable, that changes as I look at different scores. This variable is going to change. SAT scores affect the GPA. I'll call this usually an X, affecting the variable Y. So it's a little perhaps counterintuitive, maybe to some, calling this the predictor variable. This is the one that is predicting what the value of the other one is. X affecting Y. And I want to come up with an equation that, a simple equation, but something that still explains that relationship that the correlation investigation might have shown. So, in general, it's going to look like this. Like the top here, this is going to be my equation for predicting the, for example, GPA given an SAT score. So I want a nice, what we call a straight line equation, a linear equation, or linear prediction rule. Another word for prediction is regression. So I call this linear regression because I have this basic type of equation predicting my variable values. So I have two numbers that I have to find, an A and a B. The B is called I'll call it the regression coefficient that I multiply by X. And then I have this constant that I add to get the Y variable. So the Y with a little hat over it is my prediction value. And I have to eventually compare that to, maybe I have a sample of students where I have their SAT scores and their corresponding GPAs, and I can see how my prediction sort of works within that. How accurately did it predict for those students, and then I can have more confidence if I'm using it as an actual prediction in the future. So, given an SAT score X, predict the GPA Y. So for example, if I just take an example, A could be 0.3, B could be 0.004, then how do I calculate the predicted GPA? Just according to this formula, if you will. So if I take a couple of examples, if a student's SAT score is 700, I plug in 700 and I get a GPA of 3.1. Now that might not be exactly what the student would get, it's my prediction, putting me sort of in the range of what students would likely get with an SAT score like that. If I have an SAT score of 200, that's the X value, plug it in, and I get 1.1. And for an SAT score of 500, plug that in, and I get a prediction of 2.3. I'm trying to predict the future with a future student given the SAT score, so I don't really know what's going to happen until I actually see what the student does. So if I were to graph this with the SAT score, the x variable is on the horizontal axis, and the GPA, the y variable, on the vertical axis, I'm going to see that everything sits in a straight line. And that fits with the fact that that top formula or equation is the equation for a straight line. Maybe from school you might remember the form y equals mx plus b. That's the same, it just shuffles around a little bit. I still have some number times the x variable plus some other number. It looks the same way, and that's the equation for a straight line. Hence the name linear regression. Now if I look at the actual SAT scores that I could get, it might not sit all in a straight line. It might indicate that there's some straight line relationship, but it's not going to be exact. It's just a prediction to put me in the right area for my values. So how do I draw a regression line? I have to set up the vertical and horizontal axes. Then given an equation, given a prediction rule, I have to find, well, one easy way is I could find the predicted value for the y variable, for a low x variable, and mark that, and then for a high one, and then simply connect the two to make my straight line. For a straight line, I just need 2 points. Any 2 points will do, and I just connect them, and I have my line. For example, if I take this equation, just to have the numbers work out nicely, in a different example, we'll get to where I'm trying to investigate the relationship between how much sleep you get, hours of sleep, affecting the mood according to some rating scale. So let's suppose this is the linear regression line that is an accurate prediction of that. When x is 3, I pick a low number of hours slept. Then I get a corresponding y value. So if someone sleeps for 3 hours, they have a low mood rating. And if someone sleeps for longer, according to this equation, they have a higher, better mood. And I have the 2 points and I connect them. Simple as that. Just to visually see what the line is doing. Any questions on that so far? So indicating just graphically what the regression line looks like is one thing we should be able to do. And just getting 2 specific points, low and high, and just connect them is an easy way to do that. So I can then also visually see this, what I call the slope of this line, how steep it is or how flat it is. That is really indicated by this b, the coefficient of x, telling me that in this case it's a 1, that for every 1 hour extra I get the mood rating goes up by 1. So if I have a higher coefficient there, then that corresponds to a steeper line, and a lower value for b, and the line is flatter. It doesn't increase as fast. But I would need both the a and the b to specify the curve, the line exactly. Now in general, I could have, if I'm happy about this slide, I'll wait for it to wake up. In general, I could have many different equations, many different prediction rules. Each one will correspond to a different straight line. Now, given a sample of specific data values for example, in the sleep mood example, I could survey a couple of people and see how they rate their mood. Let me just fix my laptop here, or attempt to. It's severely unhappy. Why, I didn't enter. There we go, we're back. I could survey a couple of people, 1, 2, 3, 4, 5, 6, and see how, in their case, the hours that they slept related to their mood. And that gives me an idea. I mean, there's some relationship here. I'm trying to find the relationship. Now, with different regression lines, I can graph them, and they could be all over the place. There are many different rules. Some will obviously be better predictions than others. This rule 1 is probably not a good idea. That is not what the data points suggest. Whereas rule 3 and 4 do sort of seem to be in line with what those 6 points suggest. So some are obviously better than others. Now, let's investigate those 4 a little more closely. I'm actually going to go to the bottom one first. How do I determine which one is better in terms of predicting the relationship between X and Y? Well, I have to compare it to what my sample suggests. So I have my sample, different hours slept, a 5, 2 6s, 7, 8, and 10, and then the actual mood ratings that corresponded to those hours for those people. And let's suppose I have a couple of prediction rules to investigate to see which one's better than the others. So one thing that I could do is I now look at what my prediction rule says, given the number of hours slept. What does this rule say is the predicted mood for a person that slept this many hours? So some might be more accurate than others. So for each one of these 4 rules, as an example, I see the different predictions that they give. This one says, oh, it doesn't even matter how many hours you slept, your mood is always 4. This one has a little combination and uses the number of hours slept in some way. And then I have 2 more. So now when I look at the prediction values, it's hard to look at the numbers and really see, is this one better than this one? It's hard. Graphically, I might have an idea that, where was it? Zoom out. Graphically, I might suggest that rule 3 and 4 seem to be better. But between them, which one is better? It's not so easy to tell. So what we're going to do is, let's just focus on rule 1, for example, so I can zoom in. Laptop. You just have one more lecture to go. You don't want to just work with it. So that little circle is its answer of no. It does not. But hopefully that's zoomed in enough while we give it time to figure out the loop it's in. So if I look at rule 1 only, one at a time, I can compare the prediction values to the actual Y values that I got, and I can look at the deviation, the difference between them. Take the actual value and subtract the prediction value, Y minus Y hat, and I get the differences. But now when I look at those differences, yeah, okay, a lot of them are negative. Sometimes some are positive and some are negative. Here I have one positive guy, a couple of substantial negative ones, and a little negative as well. There it decided to work. So let's look at rule 2 or rule 4 just for a second and look at these deviations, these differences. If I average them out by adding them up and dividing by how many there are, I'm going to get a -1 plus a 2 plus a -1. So that sum is going to be 0. So if I take the average of all the differences, in that case it's going to be 0. but there isn't a zero error between the actual values and the prediction values. There is a difference between the prediction values and the values I actually got. So if I use these, because of the positive-negative combination of things that I could get, they're going to cancel each other out in some way, giving me a false impression of the actual difference on average between the y values and the prediction values. So for that reason, how do we get rid of the negatives? We square everything. So we're back to the squared differences, or the squared deviations. So still, it's just an indication of what the overall difference or the overall error is that I'm making, squared now. So the bigger difference will still result in a bigger number here. But now the 0.44 difference contributes a little bit, as well as the negative 0.2, they all contribute a little bit. So now they're all positive. So every little difference is going to contribute to that sum. So what I could do is look at that instead, all the squared differences, or the sum of the squares. And I see that rules 1 and 2 are fairly big. Rule 3 and 4, like I suspected when I looked at it graphically, had smaller overall squared errors. So that would be a good indication of how accurate a prediction it is overall the sample values that I have. By looking at the little differences between the actual values and the prediction values according to the rule, squaring those differences to not risk any cancellation, and then looking at that number to see which one is better. Which one is better. So I'm going to look for the one with the lowest sum of squared errors. And I'll call that the best linear prediction line. So it can be shown that if I take that approach, it's called the least squares approach because I'm squaring all of them, I'm taking the smallest one, then the A and the B in my linear regression rule, that is the best one that gives me the lowest sum of the squared errors, the formulas can be derived and they look like this. So the regression coefficient B is the more complicated one, but not really. I mean, I take all the x values, the actual x values, the difference from the x values to their average, the difference of the y values to their average, and I multiply them for each sample value that I get, and add them all up, and divide by the sum of the squares of the x values. So let's just highlight here what they say here. So I'm going to look at the deviation scores, the differences between the actual values and their averages. For each one, add up the product of the two and add them all up, divide by the sum of the squares for the x variable. The A, the constant in my regression rule, this is now the one that's going to be the best. It's going to find its path through the data points that I have to work with and try and minimize all those little squared errors. That is a little easier. That is simply going to use the B value that I get up there in an easy way using the two averages from the sample means from the x and the y variable. And again, you have access to these formulas, so there's nothing really to memorize. The only issue is just seeing how they work. So if I go back to my hour slept affecting my mood rating, trying to see what is the linear regression line, the linear regression rule that best describes the relationship between those two variables. So I have my x values in my sample and my y's for my 6 people that I surveyed. I get an average x value of 7. So I'm looking at the difference between each x score and its difference. Square that to get the sum of the squares for my x variable. Then I'm going to do the same or something similar for the y. Look at all the y values, get an average. Look at all the deviations. But I don't need to square these. I need to take this column of the y deviations with the column of the x deviations and multiply them together for each data value. That is the numerator for my b. And this is the denominator. Now in this nice convenient example, they're both 16. So I'll just zoom in here for a second. And I calculate the b, the coefficient, to be a 1. Then when I go to a, I simply take the y and the x sample means, and I get a negative 3. So my linear prediction rule, my linear regression equation, many different names for these things, is given by negative 3 plus 1. Negative 3 is the constant, 1 is the number I multiply by x. And that is the equation that's going to give me a prediction. Given the number of hours you slept, what is your mood rating? It doesn't mean that, where's my graph? It's going to be perfect. I don't expect, if I actually now sample more people, that they sit on any of these specific lines, even the best one. They're just going to hover around it. And the errors that I'm making between my prediction, the y value for the line, and the actual values that I'll observe, is overall going to be minimized. It's not going to be exactly what I'll see. I'm trying to predict the future, and there's always some variation that I can't predict, but it's trying to predict it as good as possible, given I want to fit a straight line through the data points. Any questions on this idea? Again, we're not running with this idea too much, just to give you an idea of prediction by way of a straight line.
So we're the slide that will cover all of the
let me zoom out and go to 12. 4. Whoops, there we go.
Oh, sorry, there's the chart.
Chart.
Is that just in like steps of progression to getting, because you know how with the other one, first you square the deviations and then after that you multiply it for 2?
Yeah.
So when do we do that and when do we do this?
So this was just an initial investigation to see that some lines are going to be better at describing the relationship than others.
So
and what do I call better?
Small.
The sum of the squares of the gaps. So if I look at some of these lines, if I look at line 4, the bottom of these parallel ones, 3 of these points it hits exactly, but this point not quite. So now what is the difference between, let's use this one. So this observed value point is not quite on this line. If I use rule 4 to make a prediction given this hours slept 10, I suppose, the prediction would be, well, 10, the y value that corresponds to that, according to rule 4, is going to be, I don't know, 6.5 or so. But the actual value that I got was 6. So that little difference for all the points observed, I want to minimize that, the little gaps. I want to minimize the mistakes I make. Some lines are going to have smaller overall mistakes. And some lines, like this one, is going to have a huge one. It's not a very good line. So I'm looking for the one that minimizes all those little gaps between the line and the points. Observe. Sometimes the point's going to be right on the line. Great, then I have a zero mistake, zero error. But sometimes I'm going to have a little gap. Now some of these gaps are negative, like these two, and some are positive. So if I just add up all the differences, then these two guys are going to help cancel the effect of this one. So I'm going to get a false impression of how good it actually is. So that's why we square them to make everything positive. So all these little gaps contribute to the overall rating of how good this line is. Now I'm looking for the line that minimizes this overall error that it's making, and that is the least squares line. So in this, I'm just investigating 4 lines to see some of them have a better rating than others by way of this overall sum of the squared errors. Some of them are going to be better than others. I'm looking for the best one, and those formulas give me the best one.
And when we're doing our own examples?
So now you don't do any of this.
Oh.
You just calculate the B and the A. And that gives you, let me get rid of this, that gives you your line for how you're going to predict A plus B times X. So
Oh, okay.
the best line, I just need to find these two values.
Oh, okay.
And then I have it.
Okay.
Just the rest was just to motivate, why can't I just take any line? What do I mean by the best?
Oh, okay.
Just to have an understanding of, now I don't necessarily know where this comes from, there's a little bit of math and deriving involved there, but just to understand that there is a best line. So now if I have these two values and I see how they fit next to my observed sample, they're not going to be necessarily exact predictions, but this line is still the best one, finding its way through all the data points, minimizing all those gaps. Any other line, and somewhere it's going to make bigger errors overall. So I don't know what's going to happen if I survey another person and I ask them how many hours did they sleep. Let's suppose we're over here. I make a prediction. Oh, your mood is probably like this. I don't know exactly. Their mood could be affected by something else that's not captured in this. It's just a good guess, an educated guess.
Okay, thank you.
So where are we now? In terms of calculation, that's pretty much it. The only thing is I want to say how good is my prediction. I want to have a way of saying how good it is. Now, I don't want that to be affected by the size of the numbers that I'm working with. So we have the standardized regression coefficient where I take the B, but I multiply it by this. Now this is a simplified formula, so it's going to be hard to see why that works. Especially, essentially I'm incorporating the variance in the x and the y in some way to just standardize the B a little bit. And I call that the standardized regression coefficient. So I take the two sum of the squares. The top one is the x and the bottom one is the y, the square roots, and I multiply them. So if I do that for the example, it's just going to give me an indication of how much variation between these, or let me rephrase that. How much of the variation in the y values that I'm observing is coming from the x variable. In other words, how much of the variability in the mood of people, how much of that is described by the hours of sleep. This gives me an indication of that. Same as the correlation coefficient did in the previous chapter. These two are the same. Just sort of coming from different sides. So if I calculate for my hours of sleep, the x variable, look at the sum of the squares, which we've done before, but now I also have to do that for the y variable, which I didn't need to do previously. I multiply my regression coefficient with these two numbers, square root, and I get a 0.85. So this number is the same. Let me just say it over here because I'm not sure if it's in the slide. For the case of, let's call it two-variable regression, like we're doing, the standardized regression coefficient is the same as the correlation coefficient that we've seen in chapter 11. So the interpretation is the same as well. By squaring this, I have a percentage of how much of the change in the y variable is due to the x variable. Now, we're not going to really worry about what I call multiple regression, because we'll see that, let's just go back here. What is 0.85 squared? So in my example, I get 0.85. What is 0.85 squared? Anyone want to do that for me? Ricky? So I have to look at the square, right? If you remember chapter 11. 0.722. So that means 72.2% roughly of the I don't know if it's variance of the variability in the mood of people comes from the hours that they slept, and there's still a 28 roughly percent that comes from other things. So in general, the prediction would be more accurate if I look at different factors affecting the mood of people. Maybe hours slept could be one, maybe, do they have an example? No, they don't have an example. Maybe something else, maybe length of your commute, or something else. Many different factors. Trying to get this higher. Looking at more factors in a combination to have a more accurate prediction. Now, of course, with a more complicated regression rule comes more complicated calculations. So we just want to be aware that we could do something like that, but we're not actually going to do any calculations for that in this course.
Excuse me.
Yes.
So when do we square it? The b? I call it b.
To interpret the value, the squared one, just like r squared, chapter 11.
Yeah.
They're the same for the two variable case, the x and the y case. They're the same, just different calculations. And when you look at the book, the mood example I think is in both, and you get 0.85 for both.
Are we going to be doing more than two variables?
No.
Okay.
I just wanted to be aware of it. That this isn't the end of the road, it's actually the beginning.
Okay.
And so, sorry, the 72%, is that a predictability?
That tells me there are multiple ways to interpret this. The most intuitive and easy way is, in a sense, it tells me how good the prediction is. If this is low, that tells me that the mood of people aren't really affected by the hours of sleep. A very small portion of the difference in mood values come from hours slept. If this is high, if it's like 99%, that means I don't have to look anywhere else.
Right.
Your sleep is really the only factor involved in determining your mood. So this is still good, but there's like 30% coming from other factors, which most of the time. So it's sort of it's like effect size in a way. But I don't have to think about it really like that. This is never going to be that big, because I'm never going to get that lucky, or it's unlikely that I'll get that lucky that everything is described by a single variable, single factor. That just doesn't happen. Usually it's some combination in some way, and it's hard to know what. Yeah, but it gives me a good indication of, quote unquote, how good the prediction is. That's, for us, that's the sufficient thing to write that. So I simply want to be aware of multiple regression. We're not going to do any calculations, but just to emphasize that they do have examples. Hours of sleep, how well they slept, that could be another factor. Number of dreams. I'm not sure how much that guy plays a role, but you never know. And there could be other factors. And to be more accurate in my prediction, I might have to combine these factors as predictor variables to get a more accurate prediction. Things are more complicated in general. This is a very simplified situation that we start with, but it gets the idea across. And then I would, if I could somehow find these B's, I could combine them in a very similar way. But for our purposes, I just want to be aware of this. I'm not going to ask you any questions on that. The questions come from the two-variable situation. Just be aware that this isn't the only way. In general, multiple factors combine to affect my variable. Any questions on that? We focus on the idea, and the detail really isn't that bad.